In this session, we're going to see how to solve quadratic equations by completing the square. Before we get to that, let's look at the pattern of perfect square trinomials. Perfect square trinomials come from squaring binomials, so here I have some binomials, the first one being x plus 2, the quantity squared. Remember that x plus 2, the quantity squared, means I'm going to multiply x plus 2 by itself. And remembering our FOIL acronym, multiplying the first by the first gives me x squared. And then the outer gives me 2x, but so does the inner, also 2x. And then 2 times 2 is 4. When we collect like terms, we have x squared plus 4x plus 4. And I want to note right now that the middle 4, the 4x term, came from having 2 iterations of 2x. And the last term, the 4, came from having a 2 squared. We'll just let that hang for now and move on to the next. The next one is x minus 6, the quantity squared, which we can simplify by multiplying x minus 6 by itself, unless you already want to jump into the pattern, but we're going to do that for the next one. Using FOIL, we have x times x is x squared, x times negative 6 and negative 6 times x. Those are 2 occasions of negative 6x. And then finally, negative 6 times negative 6 is 36. And we see here that we have x squared minus 12x plus 36. I again want to point out that middle term, the negative 12x, is 2 negative 6x's. And that 36 is a 6 squared. Keeping that in mind, I want you to try to multiply x plus 4, the quantity squared, without writing it out twice. Okay, so the first term squared is going to be x squared. And then I notice I'm going to have 4x, but twice, just like in the previous examples. So I'm going to write that down as 8x. And then finally I'm going to have 4 squared, which I'm going to write down as 16. And I see again this middle term, the 8x, is 2 4x's, and the last term, the 16, is 4 squared. A pattern should be emerging in your minds here. Now apply that pattern to the last one, x minus 9, the quantity squared. Squaring the first term, I get x squared, and then x times negative 9 would be negative 9x. Doubling that is negative 18x. Now again, why am I doubling it? Because it shows up twice each time we do this. Negative 9 times negative 9 is a positive 81. And we again see that the middle term is 2 times negative 9x, and the last term is 9 squared. I'd like you to notice another detail here. When we had x minus 9, the quantity squared, the middle term was negative 18x. When we had x plus 4, the quantity squared, the middle term was a positive 8x. Those two signs were always going to match, and the last sign is always going to be positive. Alright, let's see how we can use this to complete trinomial squares. Here we have some binomials, and we're asked to add the correct value to the expression to complete the square and then factor the resulting trinomial. The correct value is going to be obtained by looking at the second term. So here we have x squared plus 2x. Now if we're fitting this to the pattern that we saw in the previous slide, then the 2x is double something. Well, clearly it's double x, which has a coefficient of 1. So I'm going to add 1. And that completes the square. What square? X plus 1, the quantity squared. And you can double check that this is a correct factorization by foiling out the x plus 1 quantity squared if you like. We'll move on to the next one though. Here we have x squared minus 6x. And if this negative 6x is 2 times something, it's 2 times negative 3x. That's how you get 6, right? That means I'm going to add, now remember that whatever number was inside, the doubled, 2 times negative 3x, we squared that. So 3 squared is going to be 9. X squared minus 6 squared plus 9 factors into x minus 3, the quantity squared, remembering that the sign in front of the 6x, in this case negative, is the same sign that's going to be inside the parentheses. Now looking at the next example, x squared plus 10x, hopefully at this point, when you see that 10x, you're thinking 5. When we square 5, we get 25. And when we factor x squared plus 10x plus 25, we get x plus 5, the quantity squared. And again, that middle term is double 5x, and that last term is 5 squared. That 5 is running wild, and the positive 10x means that we have a plus inside the parentheses when we factor it. Hopefully this is getting to be old hat by now. When we look at x squared minus 16x, we're thinking 8. 8 squared is 64. X squared minus 16x plus 64 factors into x minus 8, the quantity squared, and we have factored the trinomial square. Now we'll see how we can use these patterns and this knowledge to solve quadratic equations. And our first such example is to solve y squared equals 10y plus 3 by completing the square. And let's make this look like what we saw in the previous slide. So I'm going to subtract 10y from both sides to get y squared minus 10y. And if you've been paying attention, you have the idea we might be adding something there. So I'm going to leave a gap. Equals 3. Now, in the previous slide, we looked at that middle term, well, what became the middle term, and we said, hey, this is 2 times something. I think it's pretty clear that it's negative 5y, but let's focus on this process here. Finding it's 2 times something, that's the same thing as dividing by 2. So we can take that negative 10 and divide it by 2 to get 5. That's a formal way to write it. And for what we're going to see in future examples, it'll be useful to remember that dividing by 2 is the same as multiplying by 1/2. Oops, it's a negative, isn't it? So the number of interests that we're after here from each of these thought processes is negative 5. And as you recall from the previous slide, we square that to get 25 in this case. And because this is an equation, we have to augment both sides in the same way, so I add 25 to both sides. That y squared minus 10y plus 25, that's going to factor into a square, y minus 5, the quantity squared, remembering that the sign before the 10y, in this case negative, is the same as what I'm going to put inside the parentheses. On the right hand side, we simplify, get 28, and you may be wondering, why did we just complete the square? Why do we want to write this as something squared? If you recall the square root property, if I have something squared equals number, I can square root both sides of the equation, and that's what we're after. We're completing the square so that we can square root. Let me rewrite this so it's nice and clean here. Y minus 5, the quantity squared, is equal to 28. Now I'm going to square root both sides of the equation. Hopefully you remember whenever we do that, we need to include a plus or minus, which I'm going to put in front of the square root of 28. On the left-hand side, the square root undoes the square, and we're left with simply y minus 5. On the right-hand side, we have plus or minus. Now let's see if we can simplify the square root of 28. Remember, 28 can be written as a perfect square times another factor, in this case 4 times 7. The 4 comes out of the radical as a 2. The square root of 7 is the other factor. Now we wanted to solve for y. Solve means get the variable all by itself, which I can achieve by adding 5 to both sides. I'll write that term first. This is conventionally how we write a solution like this. So I get y equals 5 plus or minus 2 times the square root of 7. And notice I don't have like terms, so I can't combine them or anything like that. Y equals 5 plus or minus 2 times the square root of 7 is how we're going to express the solutions to this equation. On to the next. Our next example is to solve 3w squared minus 6w plus 9 equals 0 by completing the square. That whole thing about taking the middle term, divide it in half and figure out what to add to both sides works really well when the first term is 1. If it's not, it throws everything off. So our first task is going to be to divide everything by 3 to get the lead coefficient to be 1. Notice on the right hand side I'm dividing 0 by 3. Even though it won't change, it's still good form. Dividing by 3 will give me w squared minus 2w plus 3 is equal to 0. And at this point we're going to subtract 3 from both sides. Let me point something out here. First we divided by 3 and then we're going to subtract that number from both sides. The order of those two steps is interchangeable. Do whichever one you want first or do them at the same time. I don't care. In any case, we have w squared minus 2w is equal to negative 3. And notice I'm leaving a gap because if you've been paying attention, you know we're going to be adding something to both sides. Half of that negative 2, let me write it formally over here. Half of negative 2 is negative 1. And then we square that thing to add it, right? So negative 1 squared, and you might be wondering, why am I showing you this? We get it. Because this format right here is going to be useful to see in a future example. In any case, we're going to add 1 to both sides. Remember, we've got to maintain the balance of the equation. And the left-hand side factors into w minus 1, the quantity squared. And the right-hand side, negative 3 plus 1 is negative 2. I want to point out again that the w minus 1 is a negative because that 2w, the linear term, had a negative in front of it. Well, we're going to square root both sides of this thing, which means we're going to throw in a plus or minus because that's what happens whenever we square root both sides of an equation. So I have w minus 1 is equal to plus or minus the square root of negative 2. Since I have a negative inside of a radical, that's going to turn out to be an imaginary number. So w minus 1 is equal to plus or minus I times the square root of 2. Adding 1 to both sides will give me w is equal to 1 plus or minus I times the square root of 2 as the solutions to this equation. Next we have solve by completing the square. Negative 2x squared plus 6x plus 3 is equal to 0. Be a good idea for you to pause this video and try to work it out. Alright, so the first thing I'm going to do is divide by negative 2. And remember, we're going to divide everything on both sides. So I have x squared minus 3x minus 3 halves is equal to 0. And then I'm going to get the constant term on the right-hand side, leaving me with a binomial that I can add the correct number to complete it. Square x squared minus 3x, leave a space, we're going to be adding, is equal to 3 halves. Now, here we have this negative 3x. It's not even, so it's a little bit harder to think about, which is why I showed you in the previous one multiplying by 1/2. So 1/2 of negative 3, well that's negative 3 halves. Take that negative 3 halves and square it. That gives me 9/4, and that's what I'm going to add to both sides. And again, we're always adding because that term of a perfect square trinomial, the last one, is always positive. Now when I factor this, I can look at when I multiplied the 1/2 by negative 3, the result of that, as it turns out, is always what's going to go inside the parentheses. So I have x minus 3 halves the quantity squared. Notice that's what happens when I cut negative 3 in half. Likewise, it's what happens when I square root 9/4 with the proper sign in front of it. In any case, on the right-hand side, we need common denominators. So I'm going to come up to the side over here, 3 halves plus 9/4. We need common denominators, so I'm going to multiply by 2 over 2. And I have 6/4 plus 9/4. That gives me 15/4. That's what the right-hand side becomes, 15/4. At this point, since I have something squared equals number, I can square root both sides. Again, that's the whole point of what we've just done. Whenever we square root both sides of an equation, we need to throw in plus or minus, and so I have x minus 3/2 is equal to plus or minus the square root of 15 over 4, which we can simplify as the numerator is simply the square root of 15, but the square root of 4 for the denominator is 2. So that works out nicely there. Finally, adding 3/2 to both sides to isolate the variable gives me x equals 3/2 plus or minus the square root of 15 over 2. If you wanted to combine these into one fraction, that would be fine, but this is sufficient as far as I'm concerned. For our next example, we have 3x squared plus x minus 1/2 is equal to 0. This time I'm going to move the constant term to the right-hand side before I divide by 3, just to show you that it makes no difference in what order we perform those two steps. Now I'm going to divide both sides by 3. Remember, to divide by 3 is the same as multiplying by a third, which might be useful when you're looking at that fraction. And so here I have x squared plus 1/3 x is how I'm going to write that linear term. Leave a space because we're going to be completing the square, is equal to 1/6 on the right-hand side there. I'm going to take that middle term and multiply it by a half, which is probably the easiest way to think of it when that middle term is a fraction. So that becomes 1/6. Whatever we get as a result of that, remember we square it before we add it to both sides. So what I'm actually going to be adding to both sides is 1/36. Remember, after we've multiplied by 1/2, that number that we get is what goes inside the parentheses. Keeping the same sign that that middle term has, we're going to write down x plus 1/6, the quantity squared. We have now factored the perfect square trinomial. Now on the right-hand side, let's come up here, 1/6 plus 1/36 with common denominators gives us 6 plus 1/36 if you like. In any case, it's 7/36. That's our right-hand side. So x plus 1/6, what am I doing? I'm square rooting both sides. And whenever we do that, remember we've got to throw in a plus or minus. So I have x plus 1/6 is equal to plus or minus, now let's simplify, the square root of 7 divided by the square root of 36. I'm going to write that as 6. So now I have x is equal to negative 1/6 plus or minus the square root of 7 over 6, which again can be combined if you like, or just leave it as is. I want to give you a geometrical interpretation of completing the square. So here I have a square with a few rectangles on the right and a few rectangles on the bottom. Let's label some dimensions here. Let's say the square has side lengths x, and then each of these little rectangles that's on the side is going to have a width of 1. So all told, that group of rectangles has a width of 3. Likewise for the bottom, that group of rectangles has a width of 3. If we consider the area of each of these figures, the area of the square is x squared. And for each of these rectangles that's attached, the width is 1 and the length is x, because it has to match the x up at the top. So each of these rectangles has an area of x times 1, so x. In other words, we have a group of rectangles that have a combined area of 3x. Likewise on the right-hand side, 3 rectangles, each having an area of x, will have a combined area of 3x. So right now this figure has a combined area of x squared plus 3x, or x squared plus 6x. Now how many little itty bitty squares would I need to add in this corner to complete the square of this figure? Yes, completing the square has a geometrical meaning. It seems to me that if I add 1, 2, 3, 4, 5, 6, 7, 8, 9, then I complete the square. Let's look at this from a slightly different perspective. Each of the sides of this completed square has a length of x plus 3. It's true for the side, and it's true for the top, x plus 3. So x plus 3 times x plus 3, that's x plus 3, the quantity squared. And we see that that's, of course, what happens when you factor x squared plus 6x plus 9. And so here we completed the square for the picture, but another way to look at it is we completed the square on the binomial, x plus 3, the quantity squared. And now to make a long video interminable, remember when we looked at negative 2x squared minus 6x plus 3 equals 0, and we ended up with x equals 3 halves plus or minus the square root of 15 over 2. And I had said that this worked out nicely because the denominator was 4 and the square root of 4 became 2. All I want to point out is if we had had something like, oh, I don't know, the square root of 15 over 7, then we would have had to rationalize the denominator by multiplying by an appropriate factor to break the denominator out of the radical. So maybe by square root of 7 over square root of 7, which would then become the square root of 105 divided by 7. The point that I want to make is not only do we have to reduce fractions, but we also have to rationalize denominators as needed.